Hi, I am Mali, and welcome to the channel. In this session, we're introducing a set of newly developed custom nodes, all of which will be integrated into today's workflow. The focus is on HiDream and a refined approach we're calling the perturbation pipeline. This method enhances traditional upscaling by introducing controlled stochastic variation, resulting in outputs that retain structural fidelity while achieving more organic texture gradients and visual coherence. This is the raw output from our HiDream pipeline. Let's zoom in a bit. It takes around 170 seconds for the entire generation. These are the results using the HighResFix method. Let's zoom in a little more. The HighResFix upscale in this case produces overly sharpened and smoothened results, with prominent hallucination artifacts in the irises and a subtle plasticity in the skin texture, ultimately diminishing overall realism. In contrast, the custom perturbation pipeline upscale delivers more naturalistic results by preserving skin microtextures and avoiding artificial iris detailing, resulting in a lifelike, photographic appearance. One of the most telling signs of an AI-generated image is its artificial perfection, overly smooth, flawless, almost plastic-like surfaces. The perturbation upscale pipeline addresses this instantly. Take this fashion portrait. For example, subtle additions of skin pores and fabric textures shift the image from clearly synthetic to convincingly photographic. Even in stylized scenes, such as a cat at a laptop, the enhanced textures reveal natural fur details and surface irregularities, giving the image a more authentic, lived-in feel. HighResFix excels at enhancing stylized content, where smoothness and precision are strengths rather than drawbacks. With dual pipelines and intuitive Boolean switching, you can apply HighResFix where it's most effective, such as in illustrations or stylized art, without compromising the integrity of photorealistic outputs. HiDream is a highly capable model. The pipeline supports intricate style transfers, enabling the application of complex visual styles while maintaining strong consistency across key elements without the use of ControlNet. This also works for non-AI trained images. However, without ControlNet or pose guidance, the results prioritize style fidelity and coherence over exact subject likeness. This means the output captures the essence and expression of the person, but may not reproduce every facial detail with photographic precision. It works best when the goal is creative transformation with recognizable traits, not strict identity matching. LanPaint works exceptionally well with HiDream, while slightly slower, the results are outstanding. Its strength lies in generating entirely new content rather than relying on blending, smoothing, or partial denoising. By using Langevin dynamics as thinking steps, it produces contextually accurate and coherent InPainting. The bidirectional guided score further enhances this by aligning masked and unmasked regions, ensuring seamless integration and maintaining overall visual consistency. Let me walk you through the complete workflow built using the new custom nodes, along with a few clever hacks I discovered while experimenting with HiDream in ComfyUI. Firstly, I would like to thank all the paid channel members on YouTube who financially support what we do. It takes a considerable amount of time to research and develop these models and innovative workflows. And we appreciate everyone's patience. Every model has its use cases and should not be compared solely based on its output. Without taking any other model's name, there are some pros you should consider by adopting HiDream, at least for image generation. The big elephant is the license. Secondly, you are getting the full model and not the distilled version. This means that you can train your LoRa on the full model, which will yield better results, and use the dev version for generation. LoRa training will require 48 GB of VRAM. All the results you saw in the intro were not using any LoRa. Lastly, the pipeline is more refined as the upscaling process requires less overhead. This is not a basic tutorial. You should be familiar with Comfy, Ollama, upscaling models, manual node installation, and so on. We got plenty of emails and some comments asking to replicate what we did with the Flux workflow, and we did exactly that, but with some new elements and a twist. Unfortunately, this model does not behave like Flux, so the entire workflow was created again from scratch, and you cannot plug and play this into the Flux workflow. To start, let's look at the custom node requirements first. Python GOS, Impact Pack, RG3, and nodes from Kajai are pretty standard. LanPaint for InPainting and Ollama for the local LLM. Also ensure you install our Control-Alt-AI nodes, and it's on version 1.1.4. The workflow uses two Upscale models. The Lexica DAT2 model is suitable for high details and sharper output. The FFHQ DAT model is the default and recommended, producing soft, natural upscaling. These models can be downloaded from openmodeldb.info. You can choose any other model, but we recommend the FFHQ DAT1 for most outputs using this workflow. This quantized version of Gemma, with 27 billion parameters, is surprisingly efficient, and we are using it for a couple of things. 1. For prompt enhancement. Second, to get the image description for the reference to the image pipeline. Lastly, to obtain a clip L and G compatible summary from the main prompt. Note that this is an instruction-tuned format version of the LLM, which is ideal for the task we want to do in the workflow. This is a 17 GB model, go lower or higher depending on your system capacity. It is important to know that the HiDream output is very sensitive to prompt. You need short, yet descriptive and accurate, prompts. If you are not getting the desired results, switch to an API LLM even for this basic task. For image-to-image InPainting and styling instructions, we found that this model was not capable, and we will use GPT via the built-in API nodes in ComfyUI. After you download Ollama, open the command prompt and type in Ollama poll and then the exact model name. This will download the model. Before starting ComfyUI, ensure the Ollama application is running in the background. The model doesn't need to be loaded. Comfy will load and offload the model in the workflow. HiDream uses quadruple clips. You need to download the 4 clips, which go inside the model/clip folder. The VAE is the same as Flux. If you don't have it, download that as well. HiDream has 3 basic models. You have full, dev, and fast. These models are available in FP16 and FP8 both. For FP16 you need 36 plus GB RAM. For the tutorial, I will be using the FP8 model. These will go in the Diffusion Models folder and can be downloaded from the Comfy Hugging Face page, and the link will be in the description. The E1 model is called the Edit model. I am not covering that in this tutorial. In testing, we found that the model is not on par for production-ready workflows. The workflow for that model is completely different. Quantized models are also available for HiDream. To use them you need to install the GUF custom node. And in the workflow, replace the GUF versions of the Load Diffusion model and Quadruple Clip Loader. Nothing else changes. I am going to build the workflow from scratch and provide explanations along the way, so it's easy for everyone to recreate or, if you are a member, understand the sections you want. Before doing that, let's look at the plan as it's a bit complicated with the logical nodes. We have inputs and settings. These 2 groups will control everything. With the workflow, you can perform text-to-image, reference-to-image, and style transfer operations. Text-to-image is a process where you enter your prompt, and the local LLM model optimizes it for HiDream, based on system instructions. Reference-to-image is what is mostly used. Drag and drop anything, the LLM takes care of the prompt, and you get something similar. Not exactly image-to-image, but using a reference image to create something new. Style transfer is actually image-to-image. I will show you some good examples and demonstrate how GPT performs compared to a local LLM in this scenario, and explain why we chose a higher-end API LLM that cannot run on consumer-grade hardware. Enabling and disabling unused groups will be manual. The settings mostly will refer to what information is passed on in the pipeline. The next step is for the local LLM to create a summary of the main conditioning. For the raw output, we have the HiDream core set of groups. Here logical switches will come for guidance, denoise, and latent. As style requires a different setting than text or reference image. More complications here as we subdivide the denoise for style in low, medium, and high settings. Once you get the raw output, you can choose one of the two pipelines for upscaling. One would be the standard latent HighResFix. And the other is our own methodology called perturbation pipeline, which is pixel-based. If you want to InPaint, then we have to use the InPaint output. The InPaint also requires a separate LLM, and again, an API LLM is recommended here. So the InPaint output will now be integrated into the two pipelines. Further complications would come because now we have two outputs integrating into two pipelines, and we need to auto-switch to the correct denoise value, conditioning, and the pipeline itself based on the settings group. For InPaint, the conditioning would be different during upscale than the main conditioning. So let's start. Add a multi-line string for the text and load image nodes. If you cannot see these options, update your Comfy to the latest version. Several new changes have been introduced in Comfy since the last video. Group these as inputs. I will set up all the settings first and then connect them later as I build the workflow. Start with the Upscale model. Disable Choose First Model and keep this setting as default. There are two integer setting nodes now. Add the advanced one. The integer setting outputs values of 1, 2, or 3. You can enable only one output at a time. This is designed for use with a three-way switch. The simple integer outputs only 1 or 2 and is useful when there are only two choices. Duplicate both nodes. One will be for style denoise and the other for InPainting. HiDream works best with some predefined resolutions. Unlike Flux, which was megapixel-based, HiDream is more like width and height. The resolutions in the node give the best output, anything else is a hit or a miss either during raw output or during upscale. Add these to the settings group and organize everything else. Build the text-to-image LLM first. Add an Ollama Generate version 2 node. Please check out these instructions carefully. If you use any other LLM model, it may not work. These are explicitly tested for the Gemma 27 billion parameter instruct model. Basically, I am asking the LLM to take whatever you input and optimize it for T5XXL and LLaMA. Disable filter thinking and enable keep context. These settings will be common for all Ollama nodes. Keep alive 0 means the model is offloaded from the GPU as soon as it generates the output. These are optional settings for more fine-tuning. I will go through them quickly, however, for the workflow, everything will be off. Mirostat sampling is for adaptive randomness control that automatically adjusts creativity versus coherence as text generates. Version 1 reacts faster to changes, version 2 provides more stability for longer outputs. ETA controls how aggressively the model adapts the surprise level, higher means quicker changes. TAU is the target level of surprise, technical word for it is entropy. Lower values make the output more predictable, higher values more creative. Use Merostat when outputs are either too repetitive, boring, or too chaotic and incoherent. This checks the last n tokens to avoid repeating recent words or phrases. Repetition penalty prevents loops and redundancy by penalizing recently used tokens, pushing the model to be more diverse. Use this when the model keeps repeating itself or falls into loops. Temperature controls how random the output is. 0.2 could be serious and factual, 0.7 is typically balanced, and 1 is creative and loose. Use high temperature for artistic descriptions, low temperature for instructions or technical prompts. Top K and Top P are used for token filtering. Top K sampling chooses randomly only from the top K most likely words. A value of 40 means it will pick from the 40 most likely next words. Top P is called nucleus sampling. It chooses from the smallest group of words whose combined probability is less than or equal to the value of P. So a value of 0.9 means pick from top 90% likely words. These are useful to avoid low quality or strange tokens while keeping diversity. Tail-free sampling removes extremely unlikely words from consideration. Lower values are stricter. Use this when getting strange, out-of-place words in otherwise good output. Controls how many tokens, words or subwords the model should generate. -1 means as much as needed. Set 100 if you want a strict 100 token output. This controls how much previous content the model can see and use while predicting the next word. A larger value allows the model to understand longer conversations, documents, or prompts. A smaller value might make the model forget what was said earlier or lose coherence in long tasks. A larger value requires more VRAM, and if running on CPU, then more RAM. Group these two nodes as Ollama settings. Connect the multi-string to the prompt. The text bridge node makes it easy to edit prompts. Comfy doesn't allow the text from the previous node to be pasted directly into the text input. Therefore, the node is not perfect due to this restriction, but manual copy and paste is a workaround. When you run the Q prompt, the output from the LLM will pass through if the text input in the bridge node is empty. This is a pass-through mode. Now if you enter anything in the text input, it will override the pass-through. To edit the LLM prompts, copy and paste them, then edit them manually. We will be adding the text bridge to all LLM nodes. The node can also act as a string node, without the need for a pass-through connection. Group these three nodes as text LLM. Duplicate these three nodes for the image LLM. Ensure that the image input is connected, and we need to update the instructions accordingly. Disconnect the prompt input connection. And the prompt would be describe the image. Output description only as a prompt. The Gemma 3 model functions as both a text and a vision model. Please note that the instructions differ. Essentially, I am instructing the LLM to provide a detailed, prompt-style description of the input image. This model is on par with image descriptions, but it cannot surpass Gemini or ChatGPT when exact instructions are provided. It's still usable though. Limit to max 2 to 4 sentences, we want shorter descriptions with as much as detail as we can get. There is a token limit in Comfy, and larger prompts will get truncated. For image-to-image style changes, we need to resize the input with one of the supported HiDream resolutions. The image resize version 2 node from KJ Nodes works very well here. This is very important. For HiDream, use bilinear for all upscaling methods. For Flux and previous models, we used to use Lanxos. However, with the perturbation pipeline, bilinear works best. Bilinear maintains a slight softness, which is crucial in achieving the desired results. Crop the resize, do not pad it. Connect the preview and input, then group the nodes. For image-to-image styling, it's best to use Gemini Pro of ChatGPT, as local models struggle with the requested changes. These are built in Comfy nodes, and I am using the balance from my Comfy account. I would not recommend using third-party nodes for the API at this time, as we have built-in Comfy nodes. Take note of the instructions. You have to tell the LLM to describe the original input as if it were in the target style. At the same time, maintaining all other visible elements and spatial relationships. The target style is what is dynamic, and since we are using 4.0, we can do a lot of creative things here rather than just changing the entire image style. Let's test a couple of instructions with the local Gemma model and the API 4.0 model to see how they perform. Between the two outputs, 4.0 performs better. It closely follows the instructions by accurately preserving the visual layout and translating every key element, from the cat's fur and eye shape to the fish and background, into flat vector terminology. It avoids poetic language and remains prompt-ready with terms like bold lines, solid shapes, and flat contrasting shades. Let's try another one. For this one, the local struggles a lot. Cat made of yarn, cinematic. GPT 4.0 clearly captures the idea of a cat made from yarn with phrases like crafted with intricate yarn loops, and maintains the cinematic tone through descriptions like reflecting light in a natural, cinematic manner. It stays consistent with the textile theme across the cat, fish, water, and background, without over-explaining or straying from the visual style. The Gemma model, while detailed, gets too technical and shifts focus to photographic terms like shallow depth of field, which leans more toward realism than cinematic yarn stylization. Let's try one last one out with Swarovski crystals. For describes the cat and fish as being made from crystal, emphasizing facets, sparkle, refraction, and the shimmering effect, all core traits of Swarovski. It also captures the lighting, reflections, and scene depth in a way that matches the crystal aesthetic, without slipping into photographic terms. The Gemma model leans more towards a literal object description and uses terms like high contrast and a sharp focus, which are better suited to real-world photography rather than stylized crystal rendering. You can experiment and get very creative results using these instructions. And this is not only about the prompt output. The thing is, HiDream picks it up very well. Short, clear prompts with accurate descriptions are the key to achieving the desired outputs. Group these 3 nodes and name it Style LLM. In the Settings group, add a Fast Group Muter node. We need to define the text, image, and Style LLM for easy mute. Follow the match title as shown. We will add more relevant groups as we progress. Choose Custom Alphabet, and you can arrange the order by typing the node title with a comma, no space. Add the new three-way switch node and connect each text bridge output from text, image, and style groups to it. Test the node via the text bridge nodes, and then connect it with the advanced integer node created earlier. When running the workflow, manually switch and disable the other groups to reduce the overhead load. And remember that the style node is an API, so don't enable it unless you are using it, otherwise, it will cost money. Duplicate all the three nodes from the image LLM group. Connect the LLM switch output, which will act as a prompt. Take note of the new instructions. Basically, I am asking it to summarize under 25 words and make it compatible with clip-L and G formatting. Let's test it. It should summarize the text prompt. Test with the other two as well. Whenever building workflows with logical switches, it's advisable to test in between as you progress. Let's address the HiDream token limit issue. HiDream originally supports 4 different text encoders: clip-L with 77, OpenClip with 150, T5XXL with 512, and LLaMA with 4096 plus tokens, each with varying capacities. However, the developers imposed a blanket 128 token limit across all of them, not due to architectural constraints, but simply because performance beyond 128 wasn't tested. This overly cautious cap was inherited by ComfyUI in its text encoding pipeline, meaning the limitation isn't ComfyUI's fault but rather a conservative default carried over from the original HiDream implementation. While you can bypass this limitation through alternative pipeline implementations, such as San Diego Dude's HiDream sampler, which creates a modified HiDream pipeline with proper per-encoder token limits, there is currently no native solution within ComfyUI itself. Since the 128 token restriction is baked into the inherited pipeline architecture, complete pipeline replacements are needed to overcome these hard-coded limitations. During extensive testing, I observed that the GPT-4o model via API triggers censorship inconsistently. The behavior appears random, without making any changes. A prompt may pass once, get flagged the next time, and then pass again on a subsequent run. Let me show you for the same cat image as shown earlier. So, I understood the reason why it is doing this. Adding as a prompt had better success rate. However, I then tried using Seth's profile image, and it failed. I then tested with other images, including animals, and encountered the same inconsistency. While a basic prompt like, "describe this image," works reliably, asking the model to reimagine the description in a specific style often triggers false censorship flags. The issue seems unrelated to content and more to phrasing. The workaround was switching to Gemini Pro, which handled the same prompts without any issues. After testing prompts generated by Gemini Pro, I found the restyle effects to be significantly better than those created by GPT-4o. HiDream is highly sensitive to prompt phrasing, and in this case, Gemini Pro consistently produced superior image outputs. My recommendation is to use Gemini Pro specifically for restyling tasks, as it yields more reliable and visually appealing results. We will now build the core nodes and integrate all the logic step by step. Add the load diffusion and quadruple clip nodes. This workflow is fully GUF compatible. For quantized models, you need the GUF version of the UNet and quadruple clip nodes. Besides these two nodes, everything else remains the same. Instead of the standard text encoding, we will use the split text encoder for HiDream. This would be for the positive conditioning. For the full model, negative conditioning is required. Use a standard clip text encode for that. Don't go overboard with negatives, something basic like this should work fine. Of course, fine-tune the keywords as per use case. The main prompt is for LLaMA and T5XXL, and the summary is for the clip L and G. Model sampling is required. Use the Stable Diffusion 3.1. For the full and fast the setting is at 3 and for the dev it is at 6. For the sampling, we are going with the Custom Sampler Advanced. As it's future-proofing for the edit model, if any version of it comes out that's actually usable. Noise, connect with the RG3 seed node. Connect a single CFG guider. The recommended value for the CFG is 5, but I prefer it at 4. We need to add a switch for the different CFG values for text, image, and style. Copy the three-way switch and use the float constant from Kajai nodes. For text and image both, the value will be 4. For style, we need stronger prompt adherence. The value for style would be 6. Connect the text, image, and style settings node with the selection setting, and test the CFG values. Add the sampler. Here you can use the following samplers, they all work. I however prefer DPM++2M. LCM basically works well for lower CFG in dev and fast models and for illustrations. Add and connect the basic scheduler. Normal, Simple, and SGM Uniform give similar results. I prefer the SGM Uniform for most use cases, and that will be the default for the workflow. KL Optimal works very well for flat style like illustrations and vectors. Linear Quadratic gives good results in some use cases. Connect an integer node for the steps. Use 50 for full. Around 28 to 30 steps for dev and from 16 to 20 steps for the fast version. Duplicate the three-way switch for the denoise. Here, we will have two separate settings. One subset setting would be for the style denoise. Low, medium, and high. And then the main switch for the text image or style. The idea of doing it this way is that if you choose style, then you further get a subchoice of doing a low, medium, or high style transfer in the image-to-image process. For style transfer strength, use 0.6 for low, 0.7 for medium, and 0.8 for high. A low value preserves more of the original content with minimal stylization and higher consistency. A high value applies stronger stylistic changes but may reduce consistency with the original image. Medium offers a balanced trade-off between style influence and content fidelity. Now duplicate it again for the main switch. Make the denoise for text and image as one, and then connect the style denoise switch with the main denoise switch. Connect the text, image, and style settings with this denoise switch and test it. When selecting a style, make sure to choose the appropriate denoise setting to fine-tune the results. For the latent, we need a switch as well. Style will be image to image. But first add the SD3 latent node and connect it with the HiDream resolution. Duplicate another three-way switch. We're using a three-way switch instead of a two-way one to synchronize the settings from a single advanced integer node, simplifying the options as text, image, or a style. For nodes like latent and CFG, however, a two-way switch is sufficient. For the style, pass the image resized output via VAE encode. Then connect the encode latent with the latent switch. Test the latent switch. The tensor output will contain values when an encoded image is used in the pipeline, unlike text prompts. The sampling nodes with the logical switch are completed. Finish with the VAE decode and the save output nodes. Now just organize all these nodes and group them. Name the group as HiDream Core. We will first test this, then proceed with the InPaint and Upscale pipelines. Also add this group for easy mute in the RG3 groups control node. Let's begin by testing the raw outputs using a simple text prompt. I'll enable only the text LLM and let it run. Since I haven't set a fixed seed, I'll use a previously generated output from the LLM to maintain consistency. This will be fed into the text bridge node to override the current LLM response. For image reference, load your image, change the setting to image, disable text LLM, and enable image LLM. It's always a good idea to run the LLM, review the generated prompt, make any necessary adjustments, and then proceed with the generation, especially in the beginning. Once you're familiar with the workflow, you can switch to one-shot runs for efficiency. Now let me show you some style examples that uses image to image. Switch the setting to style and enable only the style LLM. Let's say, cat made out of yarn, cinematic. With GPT-4o, it would often turn other elements like nearby fish into yarn as well, due to the way the prompt was interpreted. Gemini, on the other hand, handles this much more accurately, focusing the style transformation precisely where it's intended. This is on high denoise, by the way. Low denoise has different use cases, and so far ControlNet is not needed but would be helpful in more complex tasks. Let's try the style transfer on a person. The low, medium, and high denoise settings make a significant difference in the final output. You'll need to choose the appropriate setting based on your creative goal. However, this setting isn't universally consistent. What works for one style may not suit another. For instance, anime-style prompts may look best with medium denoise, while Ghibli-style prompts might require a high setting to fully capture the aesthetic. Values below 0.6 tend to preserve too much of the original image, resulting in outputs that resemble simple paintings. On the other hand, values above 0.8 often override key elements like pose and structure, generating entirely new compositions based on the prompt's style. Let's check out an example use case where you would want low denoise. And medium denoise would not work. Here I want something similar, but with psychedelic eyes. Of course it won't be the same face cause the minimum denoise is 60%, and I am not targeting the same face output. You can use InPainting for that. And there you go. Using medium here would cause color bleeds beyond the eye. So there are specific use cases for style with different denoise settings. For InPainting, we will use LanPaint, an advanced InPainting model that excels at generating new content with high coherence and realism. Unlike traditional InPainting methods that rely on blending or denoising, LanPaint uses Langevin dynamics to iteratively think through each edit, resulting in precise and contextually accurate outputs. It's slow but delivers some of the most refined InPainting results available. If you've seen our YOLO World video, where we used focus InPainting and custom models to remove subjects, that entire process becomes unnecessary here. LanPaint handles subject removal and replacement far more naturally. For InPainting, GPT-4o is highly recommended. It enhances prompts and ensures the generated content aligns accurately with your intent. The main LLM would be the prompt to modify. Summary is not needed as we will just use a single clip text encode. The instructions would go in the advanced options. Take a note of these instructions. I have designed the system instructions in a way that you just mention the changes you want in the InPaint area. For example, change cat to frog. Disable persist context, we don't need it to remember the previous prompt context. Add a text bridge node as well. A simple clip text encode is sufficient for InPainting. Instead of a preview bridge, I am taking a different approach. I will be using the load image as mask node, and would be loading the mask directly here. So basically what you do is open the mask editor from the raw output and draw and save the mask, and then load it there. The raw output will go through the VAE encode node, and then through the set latent noise mask. LanPaint has its own K-sampler and settings. Ensure the positive conditioning is from GPT-4o, and the negative conditioning is from the core node. Ensure the seed is the same for the raw and the LanPaint sampler. Change the steps as per the HiDream model. Keep the CFG at 4. Sampler and scheduler should match the ones used for the raw output. The number steps is how many thinking iterations of Langevin dynamics the model performs before each denoising step. A low value ranging from 2 to 5 is enough for simple hole filling, while 5 to 10 gives deeper refinement for tough edits. Each extra step linearly increases render time. At a value of 5, it takes about 6 minutes for a generation on a 5090. I do not prefer it at a lower value, as the InPaint quality is not on par. Prompt mode is the guidance balance. Image first anchors the fill to surrounding pixels and may downweight the prompt, making it ideal for seamless restorations. Prompt first flips the weight so the text prompt dominates, useful for character or style changes, though it can slightly degrade local coherence. For the workflow, set it as image first. Add the VAE decode and save nodes. The InPaint setting created earlier at the beginning of the tutorial won't be used here, as it's intended for upscaling. Now organize everything and let's test some generations. I will use the image reference settings. I forgot, add that group as LanPaint to the group's control. It should always be muted unless you are doing InPainting. Probably there is a spelling mistake in the group naming, let me correct it. Let's run the raw generation, then the InPaint. Let's see how the LLM performs here with the requested changes. This is exactly why we use an API-based LLM here. Local models often struggle to understand and preserve the nuanced characteristics of the replaced subject, leading to less coherent results. The API LLM, on the other hand, offers far superior contextual understanding and consistency. Extremely slow, but quality results. Passing this through the perturbation upscale pipeline will clean up everything while preserving the original context. As you can see here, the mask is no longer visible. It has blended the inpainted region seamlessly into the original image, with no harsh edges or detectable transitions. Let's try another mask, where the objective is to change the goldfishes to say maybe sharks and keep the cat as it is. Okay, so it did not change the color of the sharks. Let's adjust the prompt. Sometimes it does, and sometimes it doesn't. Hence, it is essential to check the prompt before inpainting. That worked, but let's define it as gray sharks. Perfect. Let's inpaint and see the results. This is excellent. You can see how it has perfectly blended the sharks into the scene, and even recreated the reflection of the cat with impressive accuracy. Say you want to have an eagle diving down to catch a fish in the scene, make sure to increase the mask area. This gives the model enough space to scale the eagle properly, especially since its wings will be fully extended. Let's proceed with the upscaling pipelines. This is the most complex part of the workflow, so I'm going to walk through it slowly. Don't hesitate to review this section as many times as needed. There are quite a few switches and changes happening here, but once everything is set up, it makes the rest of the process fast, smooth, and much easier to manage. Copy these 3 nodes from the core group and paste with connections. First, I'll set up the guider. The positive conditioning used for HighResFix and the perturbation pipeline will be different from what we use for the InPaint conditioning. Add a 2-way switch. Wherever there is an InPaint option, the InPaint setting switch will connect. The core guider will connect to the HighResFix perturbation input. Copy the core guider and paste with the connections. Then only change the positive conditioning to the InPaint one. Connect the switch with the guider. Now in settings, when you enable InPaint, the InPaint prompt will be used in Upscale process, otherwise it will use the prompt from the core group. Before building, let's first understand what this perturbation texture pipeline is. Perturbation here means introducing controlled, texture-matching noise across the image to simulate natural details, like skin pores, film grain, or organic surface imperfections. It's not just random noise, it's adaptive, color-aware, and scales based on your input parameters. This technique is perfect for cleaning up AI generations by adding subtle, realistic textures back into flat or oversmoothed areas, especially after inpainting or upscaling. Perturbation is pixel upscale, and we add this twice, once in the upscale image, then pass it along the K-sampler. Then again before upscaling using model. HighResFix, on the other hand, would be a latent upscale. If the raw output is perfect, you would want to maintain that quality during the upscale process. Latent upscale adds details, and the specific details it adds are not controllable. Hence, pixel upscale is preferred here. However, you would want to use HighResFix for illustrations or where you don't want that noise and prefer a clean, smooth look. This is the noise it adds to the image at the default settings. We need to adjust the settings at both stages. And this is the blended noise. The blended noise is not noticeable that much, but the AI model picks it up. So it doesn't have to be visible. Texture type defines the style and structure of the noise pattern applied, simulating specific surface details like skin, grain, or fine textures. Skin pore adds subtle, fine-grained noise with soft RGB variation to mimic natural skin texture and micro irregularities, ideal for portraits. Film grain applies broad, irregular noise with layered RGB variants and soft clustering to emulate the look of analog film grain. Natural generates layered noise across multiple frequencies to simulate complex, organic textures suitable for diverse surfaces like foliage, cloth, or painted walls. Fine detail applies high-frequency, finely scaled noise to enhance micro-level textures, ideal for boosting crispness in detailed surfaces like metal, fabric weave, or small patterns. Masking is also supported. You can apply the blended noise only to the masked area. Frequency adjusts the scale of texture repetition. Lower values give broad, soft noise, higher values sharpen micro details. Noise scale controls the intensity of the base noise. Higher values equals more visible texture. Perturbation factor fine-tunes how much the noise perturbs the base image. Great for subtle realism. Texture strength governs how strongly the texture blends into the image. 100 is full effect, lower values are more subtle. InPaint has to be integrated into both pipelines. First, let's do it for the perturbation pipeline. Connect direct pixel outputs to this switch. Now for the InPaint setting trigger, this switch ensures the correct image output flows through the pipeline. When perturbation is enabled and InPaint is off, the raw image output continues forward. But when both InPaint and perturbation are active, the InPainted result is passed through instead. This lets you dynamically route the right image. For both pipelines, we're going to upscale the image either in pixel space or latent space, by a factor of 1.25 only. Don't go higher at this stage, because the output is passed into a HiDream K-sampler. HiDream is sensitive to resolution changes and doesn't perform well if the resolution strays too far from its trained range. To achieve very high resolutions, we'll take the 1.25x output and run it through a separate 4x upscaling model afterwards. Connect the textured image output to the VAE encode. This is the blended output. We'll come back to the correct setting for the perturbation node later in the tutorial. This would be the pipeline latent switch. The perturbation settings will connect to this. Duplicate the float node for denoise. Set the InPaint denoise at 0.3, perturbation at 0.2, and HighResFix at 0.55. Set up an InPaint denoise switch. We'll explain the whole logic in a bit. Connect the perturbation and InPaint denoise along with the InPaint setting to the switch. Now set up a pipeline denoise switch. HighResFix and the InPaint denoise along with the perturbation setting connect here. So here is the logic. When both settings are off, it will use the HighResFix denoise value. HighResFix should always be at 0.55 or higher. If InPaint is enabled, the HighResFix denoise will still be used. Even though the latent is generated via VAE encoding, the purpose of HighResFix here is to enhance detail and structure. It acts as a refinement step, adding sharpness and coherence to the InPainted regions. Now, when both perturbation and InPaint are enabled, we'll set the denoise to 0.3. This is the minimum value required in the perturbation pipeline to clean up any artifacts introduced during InPainting, while still preserving the raw output. If there's no InPainting and only the perturbation setting is active, the denoise will default to 0.2. This helps maintain greater consistency with the original raw output during upscaling. Connect the pipeline denoise switch to the basic scheduler. Now we need to build the main HighResFix latent pipeline. The upscale factor here will still be 1.25x. Pass the raw latent output via the upscale latent by. Similar to the InPaint perturbation switch, create the InPaint HighResFix switch. Add another VAE encode node, and bypass the InPaint output latent before the perturbation node, and connect it with the HighResFix switch. Connect the InPaint settings here. And further connect this to the pipeline latent switch. Essentially, when InPaint and perturbation are enabled, the InPaint latent encode passes through the perturbation node to the sampling stage. But when perturbation is off while InPaint is still on, it will not go through the perturbation texture node and directly connect with the HighResFix pipeline. And this is synced with the appropriate denoise. So far the 1.25x upscale pipeline is complete. This is as far as HiDream can sample. We will now add logic for the second stage for X Upscale, which is using an upscale model. At this stage, we introduce a preview bridge for masking the second perturbation node. Earlier, the first perturbation was applied uniformly across the entire image. This was intentional, as it passed through a K-sampler, where consistent denoising was important and masking could disrupt uniformity. But now, since we're doing a pixel-to-pixel upscale, you have the option to add stronger texture selectively to masked areas. This allows for precise refinement where needed, without affecting the rest of the image. We also need a switch for the second stage upscale. If perturbation is enabled, the image will first pass through the second perturbation node for localized texture enhancement. If perturbation is off, the K-sampler output will go directly into the pixel upscale node. The perturbation setting connects here. This will connect to an upscale image using model node. Also connect the model switch setting to this node. This is now a direct 4x upscale using one of the two models defined. And that's about it. Add the save node, organize, and group all these nodes together. Name the group as HiDream Upscale. For the first perturbation texture node, these are the best settings. Ensure use mask is false, perturbation factor reduced to 0.15. Change the texture type to film grain and reduce the noise scale to 0.25. You can reduce the texture strength to 25 as well if required. The second node doesn't pass through sampling, so the setting should be less aggressive here. Change the texture type as per the image. For portraits, always use skin pour. Natural should work for most images. Reduce texture strength and perturbation factor, and keep the noise scale value at default. Enable mask only if masking. Finally, if required, add an RG3 comparer node to compare raw and upscaled output. Add the HiDream Upscale group to the group's control node and duplicate this node throughout the workflow, wherever needed, for easy group muting. Let's test the workflow and compare a portrait image between HighResFix and perturbation. First the HighResFix, then perturbation. These artifacts are normal with latent upscale. There are cases where you prefer these. In certain styles, detailing is essential, and you need to use the HighResFix. However, for natural skin and texture perturbation technique, it's a game changer. Let's change the texture type and see the results. Let's compare both upscales, which will give you a clearer idea. You can see how this result is far softer and more natural. The perturbation technique doesn't just work for human portraits, it also enhances stylized images, illustrations, and textured environments. Compared to traditional latent upscaling, perturbation offers finer control and more realism. Latent upscalers tend to introduce artificial sharpness or hallucinated detail that can break consistency, especially around subtle gradients or skin. In contrast, perturbation adds controlled, noise-based texture in pixel space, allowing for localized enhancement without altering the image's structure. It preserves the original composition while giving it depth and tactility. I employed some new techniques in this workflow, and I hope the tutorial was helpful and that you learned something new in Comfy. Until next time.